Welcome to the deep dive. Today we're taking a look at logical reasoning in these advanced AI models,
Mhm.
specifically the ones that handle both images and text, the multimodal large language models, or MLLMs.
And we're grounding this discussion in a pretty comprehensive benchmark that just came out called MME-Reasoning. It's designed specifically for this.
Right. So our plan is to unpack this benchmark, see how it actually tests logical thinking, and figure out what it tells us about where these MLLMs stand today, especially when they need to reason across different types of information.
Well, logical reasoning is just, fundamental for intelligence generally. And combining vision and language is crucial for tackling complex, real-world kinds of problems.
Exactly. And while we've seen reasoning explored in text-only models, the push now seems to be integrating that into these multimodal systems.
That's right. Because true understanding often requires reasoning about, say, a diagram alongside its description, or an image and related text.
The source material also notes that a lot of the existing multimodal benchmarks maybe lean more towards knowledge-based tasks.
That's a key point. Things like Math Vista or Olympiad Bench, they often test reasoning within specific domains like math or physics, which involves applying known facts and formulas.
So they mix knowledge and reasoning.
Yeah, whereas MME reasoning is really trying to isolate and evaluate the logical reasoning capability itself. It does this by looking at three distinct kinds of reasoning. Some newer benchmarks are starting to decouple this too, but MME reasoning makes it the central focus.
Okay, interesting. So focusing purely on the logic, what are these three types it digs into?
So the first is deductive reasoning. This is probably the one most people think of as classic logic. You start with given premises, apply rules, and derive a conclusion that must be true if the premises and rules hold. Step-by-step inference.
Okay, so like solving a standard math problem using given formulas, or maybe figuring something out in physics based on established laws.
Exactly. The benchmark uses tasks like that, math, physics problems. Also, things like geometric puzzles where you deduce relationships from a diagram, counting problems based on visual rules, or even coloring problems where constraints logically determine the solution.
Makes sense. Deriving specific answers from clear rules. What's the second type?
The second type is inductive reasoning. This is more about pattern recognition. You look at specific examples or observations, spot a trend or pattern, and then generalize or predict what comes next.
Ah, okay. So like seeing a sequence of shapes, circle, square, and predicting the next one is a circle, or number patterns.
Precisely. The benchmark includes tasks like figure series completion and identifying number patterns. It's about finding the underlying rule from examples.
Got it. And the third type?
The third one is abductive reasoning. This one's often considered, well, trickier. It involves starting with some observations and then trying to figure out the most likely explanation or hypothesis. It's like inference to the best explanation.
Okay. So less about certainty and more about plausibility.
Kind of. And the source points out it often involves exploring a really large space of possibilities. You might form a hypothesis, see if it fits, maybe backtrack if it doesn't.
The paper mentioned that humans sometimes use this even for problems that could be solved deductively, right? Like making an educated guess and testing it.
Yes, that's a really interesting point they make. For tasks in the benchmark, examples of abductive reasoning include things like Sudoku puzzles or those mate-in-one chess problems where you have to find the single best move.
Okay, I can see how those involve exploring options.
Also, analyzing electrical circuits to find a fault, interpreting biological pedigrees, logic grid puzzles like Hashi, number filling games, spatial puzzles like predicting paper cutting outcomes or moving matches problems, maze solving, and even the 24-point game where you have to find the right combination of arithmetic operations.
Wow, okay. That's a diverse set of problems that definitely go beyond just following rules. So besides these three reasoning types, the benchmark also categorizes questions by the capabilities needed.
That's right. They use 5 capability labels to get a finer-grained view. Pattern analysis, planning and exploring, spatial and temporal understanding, calculation, and causal chain analysis.
And a single question could test more than one of these.
Yes, exactly. It gives a richer picture. Pattern analysis is spotting regularities. Planning and exploring is about, well, planning sequences and checking options. Spatial and temporal deals with space and time relations. Calculation is straightforward numerical work. And causal chain analysis is about understanding cause and effect or dependencies.
Now, thinking about how the models actually do this kind of multimodal reasoning, the sources mentioned adapting techniques like chain of thought.
Multimodal chain of thought, or MC. The basic idea is getting the model to output its intermediate reasoning steps, integrating both the visual and textual information as it goes. This tends to boost accuracy and helps us understand how it got the answer.
So it's like showing your work, but for the AI, incorporating the image analysis.
Pretty much. And there are different flavors of this, some involving reinforcement learning or visualization techniques to refine those steps.
And they also mentioned adapting other RL techniques, like preference optimization.
Yes, methods based on reinforcement learning from human feedback, like GRPO, are being explored for multimodal models too. The idea is to train the model to prefer better reasoning paths. There's work cited, like MME-Reasoning and others, showing promise particularly for things like mathematical geometry or tasks needing reflection.
Okay, so that's the setup. Let's get to the results. What did MME-Reasoning actually reveal about how current MLLMs are doing?
Well, the big takeaway is that it's tough. M&E-Reasoning poses a pretty significant challenge for today's models.
Oh, really? How so?
The top scores reported in the paper were around the 60% mark. Gemini 2.5 Pro Thinking got 60.2%, Seed 1.5 VL got 59.9%. So, clearly a lot of room for improvement.
60%. Yeah, that's far from solved. Did the results show differences between those reasoning types we discussed?
Oh, absolutely. A very clear pattern emerged. Models are significantly better at deductive reasoning than they are at abductive reasoning.
That's interesting. How big was the gap?
It was quite noticeable, especially for the open source models tested. The average performance difference between deductive and abductive was nearly 10 percentage points, 9.81% to be exact. Abductive reasoning really seems to be a bottleneck.
Why is that? Why is abductive so much harder for them?
The paper suggests it's inherent to the problem type. Abductive tasks usually have a much larger solution space you need to explore. You need to generate plausible assumptions, form hypotheses, test them. It's complex.
And probably harder to create training data for, compared to deductive tasks where there's often one clear logical path.
That seems to be the challenge. Scaling up diverse, high-quality training data for that kind of open-ended hypothesis generation and verification is difficult. But the paper also stresses how important this kind of reasoning is for real discovery and complex problem solving.
Did the findings point to any other specific weaknesses?
Yes, performance was also limited in scenarios needing open-ended planning and exploration. Tasks categorized under the plan and exploration capability were particularly challenging for the models.
So even if they can follow a causal chain somewhat well, they struggle when they have to actively plan and explore in a less defined space.
That appears to be the case. It suggests current training might not be equipping them sufficiently for that kind of strategic, open-ended problem solving. Innovation might be needed there.
But there was some positive news related to models that sort of think out loud.
Yes, that was quite striking. Models specifically designed or prompted to engage in more explicit thinking, generating longer chains of thought, incorporating reflection, maybe self-correction steps, showed significantly better logical reasoning performance.
Not much better.
Quite a jump. The paper cites examples like Seed 1.5 VLT outperforming the base Seed 1.5 VL by 12.4%, and another model, O1, beating GPT-4o by 15.5% when using these thinking strategies.
Wow. So explicitly generating the reasoning steps makes a big difference on these tasks. What about those rule-based RL methods mentioned earlier? Did they provide a similar boost?
Actually, the results there were more mixed. Those methods didn't consistently outperform the base models, especially for some of the smaller 7B parameter models, where performance sometimes even dropped.
So just applying RL techniques developed for text doesn't automatically guarantee better multimodal reasoning.
It seems not, or at least not yet. The potential might not be fully realized, suggesting that maybe more adaptation or innovation is needed specifically for the multimodal context.
Okay, so let's try and wrap this up. Our deep dive into MME-Reasoning shows it's a valuable but tough benchmark. It highlights that current MLLMs are definitely better at deductive, rule-following logic.
Then they are at abductive reasoning, which requires more hypothesis generation and exploration. That seems to be a key weakness.
And tasks needing open-ended planning are also a struggle. But prompting or training models to perform more explicit, step-by-step thinking shows real promise for boosting these logical abilities.
That sums up the main findings from the source quite well, yes.
So here's something to think about. Based on all this, we see this gap, right? Models handle deductive tasks derived from clear rules reasonably well, but they falter significantly on abductive problems needing hypothesis and exploration. What does that difference really tell us about the kind of reasoning we've actually managed to bake into these models so far?